In previous lecture, we started with branching control group of instructions. There are 4 types of instructions in branching control group of instructions: jump instruction, call instruction, return instruction, and restart instruction. Jump instructions are of 2 types, which is unconditional and conditional. Call instructions are also unconditional and conditional. Return instructions are also conditional and unconditional. But restart instructions are software interrupts. So this we discussed in the previous lecture. To perform branch control group of instructions, there are 2 main things you should know. First is stack memory, second is subroutine. Stack memory deals with stack pointer. The 8085 microprocessor has stack memory. So in 8085 microprocessor, there is a stack memory, and to deal with these instructions, branching this instruction, which is branching control group of instructions, to deal with these instructions, we should know about stack memory and subroutine. So let's see what is stack memory. I'll explain it with this. So here the concept of program counter and stack pointer is explained. We know that program counter points to the next instruction to be executed. This we know. Program counter is a register available in 8085 microprocessor, and it is of 16-bit, which is used to point to the next instruction to be executed. So for example, this is set of instructions which is to be executed. The program starts from the first instruction is stored in the location 0053H. So if the first instruction is in execution, the program counter will point to the next instruction. That means in program count 16-bit register program counter, the next instruction will be stored, which is 0054. This address is of 16-bit, program counter is of 16-bit, so the next instruction, the address of next instruction will be stored in the program counter. Okay, when next instruction is in execution, when this instruction is in execution, then the program counter point to this address. When this instruction is in execution, the program counter is pointing to this address. So program counter points to the next instruction to be executed. So here a jump instruction is given. Jump instruction, which is unconditional jump instruction. This we saw in the previous lecture about unconditional jump instruction. What happens in unconditional jump instruction or conditional jump instructions? I'll explain it with the practicals which we have done. In the first practical, there is no jump instruction used. We did practical 2 also. Let's check, had we used jump instruction in here? Yeah, J and Z. We used J and Z, which is conditional jump instruction. The condition is jump on not 0. When the answer is not 0, it should jump to location 200A. Here it will jump from here, from here, from here it will jump to 200A. Okay, so it will jump here and then the program will execute. It will go on executing, and if the condition is not satisfied, if the condition is jump on not 0, what if there is 0? So it will not jump. When condition is not satisfied, it will not jump to 200A. It will execute the next instruction and it will go on, and here is the end of the program. So mostly the jump instructions, conditional and unconditional, are used to run the loops. Okay, because using jump instructions, we are in the scope of the program. We are within the program. See, J and Z, it is allowing us to jump to location 200A. The program has started from location 2000 and it's ending in 2017. So this jump instruction is jumping within the program, and mostly the jump instructions are used to run the loop. Even we can use this instruction to jump outside the program. How like here in this example, the main program is stored from location 0053 to 0057, but when the program will come to this instruction, jump 0212, jump is an unconditional jump, so it will jump outside the, you can say, outside the program to the location 0212. So jump instructions can be used to jump outside the program also. Mostly the jump instructions are used to run the loop, which jumps usually inside the program. And there are you can say call instructions, which we will be learning. Call instructions. So let's see what is call instruction. Before doing stack and subroutine, let us check the call instruction. Here the example, the call instructions can be conditional and unconditional. So what I want in this example, I want to use call instruction instead of jump, because mostly jump instructions are used to run the loops, and to jump outside the program, mostly call instructions and return instructions are used together. So let's talk about call instruction. Call is an unconditional call. Call, this instruction CALL is an unconditional call, and call can be conditional call also. In unconditional call, there will be no condition. It will not check any condition. It will simply jump. If in conditional call there is a condition like call on carry, if carry is present, then only call. When carry is not present, then call on no carry. When carry is not present, then jump. So this is conditional. These are the conditional instructions, and this call is an unconditional call. This call is an unconditional call. So it will not check for any condition, it will simply jump. So here in this example, okay, so how this call instruction is used? Call is the opcode and it requires an operand. Operand means the address where it has to jump. Like in this example, call and 16-bit address is used. That means call is the opcode and this is 16-bit address which determines where it is going to jump. So here the example which is given, this is the main program, And in the main program, there's a call instruction, which is unconditional call. So without checking any condition, it will jump to location 3000. It will jump to location 3000 and it will execute the instructions stored from location 3000. It will go on until it encounters RET. RET is a return instruction. RET is an unconditional return. And return instructions can also be conditional and unconditional. Okay, same. Return on carry, return on no carry, return on positive, return on minus. So the return instruction can be conditional and unconditional. So here, until and unless it encounters, when it encounters return instruction, it will return to from where it had jumped. It will return here to location 2003. Okay, so this call instruction, the set of instructions which are stored in a different memory, the set of instructions stored in different memory is known as subroutine. Like here is the main program starting from 2000, but here it is jumping to the set of instructions which are stored in some other memory from some other memory location starting from 3000. The set of instructions stored in different memory location starting from different memory location is known as subroutine. Okay, so here in this example I'll use call instruction. So let's talk about this. So here this is the main program. This is the main program and this program is in execution. The first instruction is in execution, then program counter should point to the address of next instruction to be executed. So program counter should have 0054. When the instruction at 0054 is in execution, then program counter should point to this address. When this instruction is in execution, then program counter should point to this address. When now it has encountered call instruction, which is unconditional call, which will make the program to jump to the subroutine which is stored from memory location 0212. So it will jump to 0212. But when this instruction is in execution, then program counter should point to 0057. But because of this instruction, the program will jump to location 0212, then program counter will have 0213. Then what about this? Where will this data go? After executing this instruction, this subroutine, if it will want to return to where it had left, how it will return? So this address, when it encounters call instruction, then this address should be stored in stack memory. So there is a difference between stack pointer and stack memory. Stack pointer is a register, 16-bit register, which is present in 8085 microprocessor. Stack is a memory. There are two types of memory, stack and queue. In stack memory, last in first out is used, which is LIFO. In queue, first in first out is used. It's like a queue of people. The person who was first in the queue will be the first to come out of the queue. Okay, so stack is a memory and stack pointer is a register. Okay, so you should keep the difference of the two in your mind. Okay, so here when it will encounter call instruction, then it will jump to location 0212 and program counter will store 0213, and this address should be pushed inside. This instruction should be pushed inside the stack memory. This address should be pushed inside the stack memory. See, this is lower order byte, this is higher order byte. The higher order byte will be stored here and the lower order byte will be stored here. Okay, it should be pushed inside the stack memory and it will jump to location 0212 and this program will be in execution and program counter will point to location 0213. When this instruction is execution, then program counter should point to location 0214. But at location 0214, it has encountered return instruction, unconditional return. Here, this return instructions do not have any operand, like do not have any 16-bit address, simply return. It do not have any operand. So as soon as the program counter will encounter return instruction, it will jump from where it had left. So it will jump here because of the return instruction. So program counter should point to next address, to the address of next instruction to be executed. Okay. I want to have RST here, RST5, and I want some instruction here. So just assume from where it had left before, when the call instruction was in execution, it jumped to this location and this address was pushed in the stack memory. And when this instruction was in execution, program counter was pointing to this address, because the purpose of the program counter is to point to the address of next instruction to be executed. When this instruction is in execution, then program counter will point to this address. When this instruction will be in execution, it will return from where it had left. It will return here. And when this instruction will be in execution, then the program counter will point to this address. And RST is end of the program. RST5 is the end of the program. Okay, so when the return instruction was in execution, then program counter should point to this location because it had to return from where it had left. Then program counter should point to this address. Then what happens? Then 57 will be popped out and 00 will be popped out and stored in the program counter. When it returns from where it had left, then in program counter from the stack memory, the address which was pushed will be popped out and stored in the program counter. Okay, so what exactly is happening here? When first instruction is in execution, then program counter should point to location 0054H. When this instruction in execution, then program counter should point to 0055H. When this instruction in execution, then the program counter should point to 0056H. When this instruction is in execution, okay, so when this instruction is in execution, then program counter should point to 0056, right? And just assume this is the stack memory. This is the stack memory in which already some data is already stored, and stack memory is from 000A to 0004. You know, when you push the contents in the stack memory reduces. The size of the stack memory is determined in the start, already determined in the start. So the size of the stack memory is, see, the location is reducing. The stack memory is from 000A to 0004. Okay, so this is the size of the stack memory. When you fill the stack memory, when you push the contents in the stack memory, then the size of the stack memory gradually reduces. So just assume that in the stack memory already few contents are stored. At location 00A, 00 is stored. When you subtract 1 from 000A, you will get 009, which is 51. Then it will decrement by 1. It will become 008. In 008, 00 is stored. Then in 0007, 80 is stored. So currently the stack pointer, this address is stored. This address is stored in the stack pointer, as you can see. When this instruction is in execution, then program counter will point to this address. Okay, and there is a stack memory, and then in that stack memory the already few contents are stored, and the stack memory is filled to location 004. So stack pointer will hold this address, this 16-bit data, which is 0007. We know stack pointer is a register in 8085 microprocessor, which is of 16-bit. And when this program is in execution, then program counter should point to location 0057. But here there is a call instruction where the main program will jump to the subroutine starting from location 0212. So when this instruction is in execution, then program counter should hold 0057. It should be 0057. This should be 0057. When this instruction is in execution, in program counter 0057 should be there, because program counter points to the next instruction to be executed. But this instruction will compel the main program to jump to location to the subroutine starting from 0212. Then program counter should point to location 0212. When this instruction is in execution, then program counter should point to location 0212. Then what about this? what if after executing this set of instructions the program will want to return to where it had left? So this address should be stored somewhere. So this address is stored in the stack memory. So when this instruction in execution, then the program counter should point to location 0057. Then the contents of this program counter will be pushed in the stack memory. The higher order byte will be stored here and the lower order byte will be stored here. And then the main program will jump to location 0212 in program counter. 0212 is there. When this instruction is in execution, then program counter should point to location 0213. And here in stack pointer, what was there? 0007. But when we pushed the contents of program counter into the stack memory, then from 0007, 00 was stored at location 006, and when we decrement it, it will be the address will be 005 and 57 will be stored at location 005. Then stack pointer will point to in stack pointer 0005 will be stored. So this is the purpose of program counter and stack pointer. Now if as I had told you that size of the stack memory is fixed, the programmer determines the size of the stack memory by using the instruction LXI SP. Here in this case LXI SP 000 B. So the stack pointer is initialized from location 000B. So in stack pointer, what is there? In stack LXI means store this 16-bit data in the stack pointer. So in stack pointer 000B is stored. Okay. So if in stack pointer 00B is there, then the data should be stored from location 00A. Like here you can see the stack pointer was pointing to location 007 when there was a push, when we had to push contents of program counter into the stack memory, then 00 was stored from where? 0057 was stored from where? From location 006, 1 less than 007. So if in stack pointer 000B is stored, then the content will start getting stored from location 1 less than from this location. When you subtract 1 from 00B, we get 00A. So the contents will start getting stored from location 00A. If in stack pointer 000B is there, then the contents will start storing from location 00A. Okay, so when you want to determine the size of the stack memory, this instruction should be used. This instruction LXI SP, which is stack pointer, and from where you want to initialize the stack memory. So I want the stack memory should start from 00A, so this in stack pointer 000B should be stored. Okay, so when you want to push contents from some register pair or from some register to the stack memory, then push instruction is used. Push PC. The contents of program counter will be pushed in stack memory. When you want to pop, when there is a return instruction, then it should be back to the location from where it had left. It should be back to 0057. Then this content should be popped into the register pair. So pop instruction is used. Pop PC. So 0057 will be stored in program counter by using the pop PC instruction, and then program will continue executing from location 0057. But to initialize the stack memory, we will use this instruction, but push and pop instruction we do not have to specify. This is performed by return instruction automatically. And call instruction. When call instruction is executed, then this address will be pushed into the stack memory automatically, and it will start executing the set of instructions stored from location 0212. When it will encounter, when this instruction will be encountered, then it will automatically, then the stack contents will automatically be popped out. Will not have to use this instruction. It will automatically be popped out into the program counter, and it will be back to this location. So this I was just showing you the example of push and pop instructions, because push and pop instructions are available, which we will be learning in forthcoming topics. Okay, but in case of call instructions we do not have to explicitly use the push, and in case of return instruction we do not have to explicitly use the return instruction. Okay, it is implicit, it is automatically done. The programmer will not have to use the push and pop instructions after call instruction. Call instruction will automatically push the contents of program counter into the stack memory, and return instruction will automatically pop out the contents of stack memory into the program counter. Here you can see this, right? This should be actually 7 in the diagram. It was 6 which was wrong. It should be 7. Okay. One more thing I want to tell you is when these contents will be popped out, when 57 and 00 will be popped out in the program counter, then the stack pointer will be decremented. Then the stack pointer will be decremented, and it will point to, again it will be back to 0007. When it will be popped out, then program counter will, sorry, not decremented, incremented, sorry. Here it decrements. When we push contents into the stack, it decrements. When we pop out the contents from the stack, it increments. So when this will be popped out, it will be incremented by 1, and when this will be popped out, it will be incremented by 1, and in stack pointer again there will be 0007. Okay, so this is the concept of program counter, stack pointer, and stack memory. Okay, see, the same thing has been told, that when the contents will be popped out from the stack memory and it will be back into the program counter, then the stack memory will be incremented, and stack pointer 0007 will be stored. Stack pointer will point to the address of the stack memory. Okay, so this is the concept of program counter, stack pointer, and stack memory. So let's see what's written in the theory here. Stack, what's written about stack. So the stack is an 8085 based microprocessor system. The stack in an 8085 based microprocessor system can be described as a set of read-write memory location specified by the program in the main program. So stack, when we are talking about 8085 microprocessor, so in 8085 microprocessor, what is stack? In stack we can read and write the data. When we were performing push and pop, when we were pushing contents in the stack memory, we were writing in the stack memory. When we were popping out the contents from the stack memory, we were reading the data from the stack memory. So in 8085 microprocessor, stack memory can be seen as read write memory, or you can say in the stack is a memory. You can consider the stack memory as a set of read-write memory locations. These are the memory locations. We can read the data from these memory locations. We can write data to these memory locations. Okay. These memory locations are used to store binary information on temporary basis during the execution of the program. So these stack this stack memory, this addresses of stack memory are used to store the data temporarily. This was temporary data which was stored in the stack memory, which was popped out when the work was done. This data was stored temporarily. So these memory locations are used to store the data or store the binary information temporarily during the execution of the program. This thing was done when the program was in execution, during the program execution. One more thing I want to explain is, I had told you in stack there is last in first out, LIFO. So these two data were last in when pop instruction was used. So these two were the last in which was first out. When pop PC will execute, then the contents which is last in will be first to be out of the stack memory. So stack memory follows last in first out. The beginning of the stack is defined in the program by using the LXI-SP 16-bit address instruction. So this instruction which I had explained, this instruction is used to define the beginning of the stack. This instruction is used to define the beginning of the stack. The stack is starting from 00B. So if stack is starting from 00B, then the content will start getting stored from location 00A, 1 less than 00B. When you subtract 1 from 00B, you will get 000A. Okay, the beginning of the stack is defined in the program by using this instruction, which loads 16-bit memory address in stack pointer register of the microprocessor. So this instruction stores the 16-bit address. This instruction stores the 16-bit address into the stack memory. In 8085, when we initialize stack pointer, here we initialized the stack pointer from location 000B. So when we initialize stack pointer, then storing of data bytes begins from a location with the address 1 less than the SP contents. So that's what I was telling you. The storing of data will begin from location 00A, 1 less than the contents of stack pointer, 1 less than 00B. As we go on storing more and more data, the stack pointer goes decrementing. as we stored these two data in the stack memory, it decreased from 0007, it went to 006, then 005. Okay, so when we store the contents in the stack memory decrements. That's what it's written here. The stack pointer contents decrement. Thus the stack grows from higher address to the lower address. So stack is growing from higher address to the lower address, from 0008 to 000 here, from 0008 to 0005, from 0008 to 005. It is reducing higher address to lower address. Therefore, normally while writing 8085 programs, users initialize SP at the highest available user read write memory location. So when writing the 8085 programs, the user should decide the highest possible read write memory for the stack pointer, because the size of the stack pointer is fixed. If this stack memory is filled, no more data can be stored until and unless something is popped out from the stack memory. The size of the stack is thus only limited by the available memory. So size of the stack is limited. In 8085, we have following instructions to store the data and retrieve it back from the stack. So to store the data in the stack memory, we should use push instruction. And to retrieve back the data stored in the stack memory, we should use pop instruction. To store data in the stack memory, push instruction should be used. To retrieve this data which was stored in the stack memory, pop instruction should be used. Okay, so push to store operand contents on stack, pop to load from stack into operand. What is written in push? See, in push to store operand contents on stack. Push, this is the operand, program counter is operand. So to store operand contents into on stack. Pop to load from stack into operand, to load from stack into operand. Operand can be any register pair like B, C, D, E, HL, program counter. Okay. We will discuss this instruction. Okay, in the forthcoming sections, we will be discussing these instructions in detail. One of the important uses of stack is done while executing a subroutine. We use this is known as subroutine. When this instruction gets executed, when the call instruction gets executed, then it will jump to location 0212. So the set of instruction which is stored in different memory location is known as subroutine. So this is subroutine. So the concept of stack is mostly used in case of subroutine. One of the important use of stack is done while executing a subroutine. But what exactly is a subroutine? So let us now see what does a subroutine exactly means and how it is executed. So here the subroutine has been explained. So this we will do in the next lecture. For today we will stop here.